4.37 light-years. That's the distance to Alpha Centauri, our closest stellar neighbour. Close enough that if you could somehow travel at 1% the speed of light, wildly beyond our current technology, but not prohibited by physics, you'd reach it in under 500 years. In cosmic terms, Alpha Centauri is practically next door. We've been observing it for centuries. Ancient astronomers knew it as one of the brightest stars in the southern sky. Modern astronomers mapped it with increasing precision. We know it's actually 3 stars orbiting each other. Alpha Centauri A and B are sun-like stars locked in a binary dance. Proxima Centauri, a small red dwarf, orbits the pair at a distance. We've found planets. Proxima B orbits in the habitable zone of Proxima Centauri, a rocky world where temperatures might allow liquid water. The system has been studied exhaustively. Catalogued, understood, or so we thought. Then in late 2023, the James Webb Space Telescope pointed its infrared eye at Alpha Centauri for what was supposed to be routine characterization. Webb was tasked with studying the atmospheres of known exoplanets in the system, looking for biosignatures, chemical traces that might indicate life, standard science, important but not expected to be revolutionary. Webb had already found surprises around distant stars, early massive galaxies, strange atmospheric compositions. But Alpha Centauri was different. Close, familiar. We knew this system inside and out. What could possibly surprise us? The data came back and something was wrong immediately. Not wrong with the instruments. Wrong with what they were seeing. There was a signal, a distinct infrared signature that shouldn't exist. Not from the stars themselves, not from any known planet, not from debris or dust, from something else, something between the stars, something that glowed in infrared wavelengths with a spectrum unlike anything in our astronomical catalogues. The initial reaction was instrument error, cosmic rays hitting the detector, scattered light from the bright central stars creating artifacts. Teams checked and rechecked. They processed the data multiple ways. They compared to calibration observations. The signal persisted. It was real. Then they checked archival data, old observations from Hubble, from ground-based telescopes, from infrared surveys conducted over decades. And here's where it got strange. The signal was there too, faint, barely above noise thresholds, easy to miss or dismiss as instrumental effects. But present, going back 40 years, this thing, whatever it was, had been sitting in the Alpha Centauri system the entire time we'd been looking at it. We just hadn't noticed. We hadn't been looking at the right wavelengths with the right sensitivity. Webb's advanced infrared capabilities brought it into focus for the first time. But it wasn't new. It had been there all along. Within weeks the story leaked. Not the full data, not the analysis. Just whispers that Webb had found something unexpected at Alpha Centauri. The internet exploded with speculation. Aliens. Obviously aliens. What else could emit mysterious signals from our nearest stellar neighbour? Scientists tried to downplay it. Premature to speculate. Need more data. Probably natural phenomenon. But the speculation wouldn't stop because the scientists themselves couldn't explain what they were seeing. Private conversations at conferences revealed deep puzzlement. This wasn't like discovering a new type of star or an unexpected planet. This was something that didn't fit any category. Not a star, not a planet, not an asteroid or comet, not interstellar gas or dust behaving normally. Something else. The spectrum was the key piece of evidence. Every object in space has a spectrum, a fingerprint of wavelengths it emits or absorbs. Hot stars emit black-body radiation, peaking at short wavelengths. Planets reflect their star's light and emit thermal radiation at longer wavelengths. Gas clouds emit and absorb at specific wavelengths corresponding to electronic transitions in atoms and molecules. We can identify what something is made of and how hot it is from its spectrum. This is basic spectroscopy, textbook science. We've been doing it for over a century, but the spectrum from this object didn't match anything. It wasn't thermal, It wasn't reflected starlight. It wasn't atomic or molecular emission lines. It was something else entirely. A continuum with strange features, peaks and valleys at wavelengths that made no sense. Like seeing a colour that doesn't exist in the rainbow. Temperature was another puzzle. The object was emitting as if it were warm. Not hot like a star, not cold like empty space. Warm, room temperature, warm, 300 Kelvin, give or take. This is bizarre for something in interstellar space. Space is cold, interstellar medium is a few degrees above absolute zero. Even in a stellar system, unless you're very close to a star, temperatures plunge. This object was between the stars, not orbiting close to any of them, yet somehow maintaining a temperature you'd find comfortable. Where was the energy coming from? Stars emit energy from fusion. Planets reflect starlight and have residual heat from formation and radioactive decay. This had neither. It was generating or retaining heat through some mechanism that wasn't obvious. Size was impossible to determine directly at first. It was too far for Webb to resolve spatially, but they could estimate from the total luminosity and assumed temperature. The calculations gave answers that didn't make sense. If the thing was at the distance of Alpha Centauri and emitting as much infrared as observed, it had to be large, kilometers across at minimum, possibly much larger depending on assumptions, not planet-sized, but far bigger than any spacecraft we've ever built, bigger than asteroids typically get unless they're the size of small moons. And the shape was wrong too. The light curve, how brightness changed over time, suggested it wasn't spherical. It was elongated or irregular, tumbling or rotating in a way that modulated its observed brightness. Follow-up observations were rushed. Every telescope that could see Alpha Centauri was pointed at it. Radio observations, optical, X-ray, more infrared at different wavelengths. Each added pieces to a puzzle that only became more confusing. No radio emissions, nothing in optical except extremely faint possible reflected light. No X-rays, just this infrared signature. And now that people knew where to look, more details emerged. The object appeared to have structure, not just a blob. There were variations in brightness across its surface or volume, hot spots, cool spots, patterns that changed over hours to days. This suggested activity, something dynamic happening. Not just an inert object floating through space, but something active, something that might even be engineered. The word nobody wanted to say out loud, but everyone was thinking. This could be artificial, a probe, a spacecraft, something constructed by intelligence and sent to Alpha Centauri. By whom? Not us. We've sent nothing to Alpha Centauri. The fastest object we've launched, Voyager 1, has been travelling for nearly 50 years and hasn't even left the solar system's influence. It would take tens of thousands of years to reach Alpha Centauri at its speed. And this object had been there for at least 40 years, based on archival data, probably longer. We didn't build it, so if it's artificial, someone else did. Someone with the capability to send objects between stars. Someone who chose Alpha Centauri, our nearest neighbour, as a destination. Someone who might know we exist. Someone who might be watching us right now. The scientists tried to remain calm. Extraordinary claims require extraordinary evidence. Artificial origin is the most extraordinary claim possible. Every natural explanation must be exhausted first. But as the data accumulated and natural explanations failed one after another, the possibility that couldn't be named became harder to ignore. We had looked at Alpha Centauri thousands of times. We thought we knew everything about it, then we looked with new eyes, and we saw something that shocked us. Something that shouldn't be there, something that we still don't understand. And the most disturbing part, it had been there the whole time, waiting, watching, while we remained oblivious, staring at our neighbour, without seeing what was right in front of us. Until now. Astronomers have a taxonomy for everything in space. Main sequence stars, red giants, white dwarfs, gas giants, ice giants, rocky planets, asteroids, comets, meteoroids. nebulae, galaxies, quasars. Centuries of observation have created categories that encompass virtually everything we've found. When you discover something new, you identify what category it fits into. New planet? Characterize its mass and orbit, and it slots neatly into the planet category. New type of star? Measure its spectrum and luminosity, and it goes into the stellar taxonomy. The system works because nature seems to create the same types of objects over and over. Stars are fundamentally similar everywhere. Planets follow patterns. Even exotic objects like pulsars or black holes fit into categories once we understand them. But this object at Alpha Centauri fits nowhere. It's not a star. Too cool. Stars generate energy through fusion and shine across the spectrum. This emits only in infrared, and barely at that. It's not a planet. Wrong spectrum, wrong temperature distribution. Planets reflect their star's light with spectra that shows stellar features plus any atmospheric absorption. This shows neither. It's not a brown dwarf, those failed stars that are too small to sustain fusion. Brown dwarfs have characteristic spectra dominated by molecular absorption from methane and water vapor. This doesn't. It's not a comet or asteroid. Those are solid bodies that reflect light and emit thermal radiation. The spectrum doesn't match. It's not a dust cloud or gas nebula. Those scatter starlight and emit at specific wavelengths. This is different. The scientific papers trying to classify it are exercises in frustration. Each paper proposes a category, then methodically rules it out. Could it be an unusual brown dwarf? No, because the spectrum lacks methane absorption. Could it be a very cold planet somehow ejected from the system? No, because the thermal emission is too uniform. Could it be a ring of debris? No, because the light curve doesn't match orbital mechanics. Could it be background contamination from a distant galaxy? No, because it moves with proper motion consistent with the Alpha Centauri system. It's there, in the system, real, but unclassifiable. Temperature is the first major anomaly. 300 Kelvin room temperature. For an object in interstellar space, not close to any star, this makes no sense. Calculate the equilibrium temperature of an object at that location based on stellar radiation. It should be maybe 50 Kelvin. Frozen. To maintain 300 Kelvin requires an internal heat source or some mechanism that retains heat impossibly well. What could that be? Radioactive decay? Insufficient. You'd need impossible amounts of radioactive elements. Tidal heating from gravitational interactions? It's not close enough to anything to experience significant tidal forces. Residual heat from formation. It would have cooled billions of years ago. Every natural mechanism for heating fails to explain the observed temperature, unless it's not in thermal equilibrium. What if the object has low thermal conductivity? What if it's insulated somehow? Imagine a sphere with a hot core and an insulating shell. The surface could be warm while not actively generating heat if the insulation is good enough. But what natural process creates insulating shells around objects in space? And what heated the core? This is already sounding contrived. You're inventing properties and structures specifically to explain the observation. When you have to add multiple ad hoc features to make a natural explanation work, maybe it's not the right explanation. The spectrum is equally baffling. Spectroscopists have compared it to every known spectrum database, natural and artificial. It's not a black body, it's not reflected starlight, it's not emission from any known molecule or atomic transition. It's not industrial or spacecraft signatures, not that we have good references for alien spacecraft, but it doesn't match human-made spectra either. The features in the spectrum appear at specific wavelengths that don't correspond to any chemical element or compound. This is deeply weird. Spectra come from physics. Atoms and molecules have energy levels. Photons are emitted or absorbed when electrons transition between levels. These transitions happen at specific wavelengths determined by quantum mechanics. Every substance has a signature spectrum. But this doesn't match any substance. Could it be exotic chemistry? Molecules we've never made in a lab, operating under conditions we've never studied? Possibly, but we understand quantum mechanics. We can predict what spectra should look like, even for molecules we haven't synthesized. The features in this spectrum don't match predictions for any plausible molecule. They could be complex mixtures creating coincidental features, but you have to work very hard to make that explanation fit. Again, it requires adding complexity, specifically to force a natural explanation. The structure is another problem. High-resolution imaging shows the object is not uniform. There are brightness variations across its extent, regions that are warmer or cooler, patterns that change over time. Natural objects can have structure, surfaces have geology, atmospheres have weather, but this doesn't look like either. The patterns are too regular, too geometric. There are suggestions of linearity, straight edges or boundaries between bright and dark regions. Nature creates straight lines occasionally, crystal faces, but in kilometre-sized objects floating in space. That's unusual, very unusual, and it's active. The light curve shows variations on multiple timescales. Hours, days, weeks. This suggests processes happening on or within the object. Rotation alone wouldn't explain all the variations. You'd need internal activity, heat transport, changing surface properties. Something dynamic. Asteroids are geologically dead. They don't have internal processes. Planets can be active, but that requires size and internal heat sources. This object apparently lacks. Comets are active when near the Sun, outgassing as ice sublimates. But this is far from the stars and shows no signs of gas emission. What makes it active? Size estimates keep refining as more data comes in. Current best guess is somewhere between 10 and 100 kilometers in longest dimension. That's sizable. Smaller than a moon but larger than most asteroids. Shape is elongated. Aspect ratio maybe 3:1 or 4:1. Cigar-shaped or cylindrical. Rotation period around 30 hours based on light curve periodicity. This is slow for an asteroid. Most rotate faster, but consistent with a large object. Mass is completely unconstrained because we can't see gravitational effects on anything nearby. It could be dense metal, or porous ice, or mostly empty. No way to tell without seeing it pull on something or measuring its response to forces. Every attempt to classify this object runs into contradictions. It's too warm but has no heat source. It has structure but no obvious geology. It's active but not in ways natural objects are active. Its spectrum matches nothing. Its size is awkward, too large for a spacecraft. By human standards, but too small for a planet. It doesn't fit anywhere. And that's what makes it so compelling and so frightening. We've observed billions of astronomical objects, catalogued hundreds of millions, created taxonomies that encompass the incredible diversity of cosmic phenomena. But this one thing, sitting 4 light-years away in the most observed nearby star system, defies every category we've created. It's either something natural that operates by physics we don't understand, or it's something that shouldn't exist naturally, something that required intent and purpose to create, something artificial, and if it's artificial, everything changes. Once the Webb data made the object undeniable, researchers started digging through archives with new eyes. Decades of astronomical observations, millions of images and spectra, most taken for different purposes, studying the stars rather than looking for faint objects between them. But the data existed, stored in digital archives at observatories around the world. If this object had been there all along, it should appear in old observations, faint maybe, easy to overlook, but present. Finding it would tell us how long it's been there, whether it's moved, whether its properties have changed, and that's exactly what they found. The earliest confirmed detection dates to 1981. The Infrared Astronomical Satellite, IRAS, surveyed the entire sky in infrared wavelengths. Its mission was mapping infrared sources, stars, galaxies, nebulae. It created a catalogue of hundreds of thousands of infrared sources. And buried in that data, in the Alpha Centauri field, there's a point source, faint, just barely above the detection threshold, ignored at the time because it wasn't bright or interesting enough to follow up. But it's in the right location, and it has the right spectrum within the limited resolution IRAS had. It's the object, 1981, that's 43 years ago. The object has been in the Alpha Centauri system for at least that long, probably longer. IRAS was not sensitive to very faint sources. If the object was fainter before 1981, IRAS would have missed it. So 43 years is a lower limit. Could be hundreds or thousands of years. Could be much longer. We don't know when it arrived, only that it's been there throughout the modern era of astronomy. Tracking through subsequent observations shows something interesting. The object appears in infrared surveys from the 90s. 2-micron all-sky survey, 2MASS, caught it, again barely. Again catalogued as a faint point source and ignored. Spitzer Space Telescope observed Alpha Centauri in the 2000s. There it is in the data, slightly brighter in some wavelengths. Herschel Space Observatory, another infrared telescope, imaged the region in the early 2010s. Present again. Each observation added a data point. Each showed the object was persistent, real. Not a transient phenomenon or a fluke detection. But here's what's remarkable. The object has moved, not randomly, not like something drifting on stellar wind or gravitational perturbations. It's moved with the Alpha Centauri system. Alpha Centauri has proper motion, apparent movement across the sky due to its actual motion through space relative to the Sun. Over decades, that motion is measurable. The stars shift position, and this object has shifted with them. It's kept the same position relative to the stars. This proves it's gravitationally bound to the system. Not just passing through, not background contamination. It's there, in orbit, or at least moving with the system in a way that makes it a member. Calculating the orbit is difficult because we're seeing it in projection. Two-dimensional positions on the sky when the real orbit is three-dimensional. But astronomers have techniques for this. Statistical methods, Bayesian inference, they've constrained possibilities. The object appears to be in a wide orbit around the barycenter of the Alpha Centauri system. Possibly tens of thousands of astronomical units out. That's far. In the Oort cloud equivalent, if Alpha Centauri has one, the orbital period would be tens of thousands of years. So we've only observed a tiny fraction of one orbit, but the motion is consistent with being bound to the system rather than passing through. Has it changed? This is crucial. A natural object should be relatively stable. An artificial object might show signs of activity, aging, damage. Comparing brightnesses across 4 decades shows variations. But that's tricky, because different telescopes have different calibrations and sensitivities. You can't directly compare IRAS brightness to Webb brightness and conclude the object got brighter or dimmer. Too many systematic uncertainties. But within those uncertainties, the object seems roughly stable. It's been emitting at similar levels for decades. No obvious trend of brightening or fading. No sudden changes. Consistent behavior. This actually makes it more mysterious, not less. A natural object could be stable, but so could a well-designed artificial one. Stable operation for decades doesn't distinguish between possibilities. Spectral evolution is more informative. Webb's spectrum can be compared to earlier infrared spectra from Spitzer and Herschel. The wavelength coverage differs, so you can't do a perfect comparison, but where they overlap, the spectral features are the same. The object hasn't changed its spectrum over 15 years. That's the time span where we have decent spectral data. Whatever processes produce that unusual spectrum have been stable. No signs of evolution or aging. Again, this could be natural stability, or it could be engineered stability. Doesn't tell us which. One intriguing detail from the archival search, there might be older detections. Photographic plates from ground-based telescopes in the mid-20th century show the Alpha Centauri region. These plates are stored in archives. They can be scanned and digitized. Some researchers have done exactly that, looking for the object in plates going back to the 1950s and 60s. The results are ambiguous. At the limit of photographic sensitivity, there are hints, faint spots in locations consistent with where the object should be, but they're not definitive. Could be the object, could be grain in the photographic emulsion, could be background stars or artifacts. The evidence is marginal. If the object is there in 1950s plates, it's been at Alpha Centauri for at least 70 years. That's within living memory. People alive today were alive when this thing, whatever it is, was already present. But 70 years is also frustratingly recent on cosmic timescales. It tells us almost nothing about origin. Did it arrive 70 years ago? 100 years? 1,000? We can't say. All we know is it's been in the neighbourhood for decades at minimum, silently orbiting our nearest stellar neighbour, emitting its strange infrared signal, visible to anyone who looked in the right way with the right instruments, but unnoticed, unremarked, a mystery hiding in plain sight. The archival evidence does one important thing. It rules out this being a recent arrival. It's not something that showed up yesterday. It's been there, part of the Alpha Centauri system, or at least visiting it for a substantial period. This changes the implications. A transient visitor could be a comet from another system, natural flotsam drifting through the galaxy. But something that's been there for decades, orbiting, stable, that's different. That suggests permanence, purpose. Whether natural or artificial, it's not a random interloper, it's established there. Which raises a new question. If it's been there so long, why haven't we noticed it until now? The answer is humbling. We weren't looking. We assumed we knew what was in the Alpha Centauri system. Stars, planets, maybe some dust. We looked at those. We studied those. We didn't look at the empty space between. We didn't scan the outer system with sensitive instruments at the right wavelengths. We were blind not because the object was hiding, but because we didn't bother to look. And that oversight might be the most shocking part of this whole discovery. 300 Kelvin, say it out loud, 300 degrees above absolute zero, 27 degrees Celsius, 80 degrees Fahrenheit, room temperature. This is the approximate temperature of the object based on its infrared emission spectrum. And this is where physics starts to break down, because there is no good reason for something in the outer Alpha Centauri system to be this warm. Let's work through the thermodynamics and see where it leads. Start with basic principles. Objects in space reach equilibrium temperature based on energy in versus energy out. Energy in comes from radiation. Stellar light, cosmic microwave background, maybe particle impacts. From stellar wind though, that's negligible at these distances. Energy out is thermal radiation. Every object emits infrared proportional to its temperature, raised to the fourth power. Stefan Boltzmann law. At equilibrium, energy in equals energy out, and temperature stabilizes. Calculate the equilibrium temperature for an object at the estimated distance from Alpha Centauri's stars. The stars are bright, but the object is far away. Tens of thousands of AU puts it well beyond the main stellar radiation zone. The amount of stellar light reaching it is tiny. Run the numbers assuming reasonable albedo and emissivity. You get an equilibrium temperature around 50 to 70 Kelvin. Very cold, not 300, not even close. The object is receiving nowhere near enough stellar radiation to maintain its observed temperature through equilibrium processes. So it needs an internal heat source. What could provide heat? Radioactive decay is the obvious natural answer. Earth's interior stays warm partly from radioactive decay of uranium, thorium, potassium. Could this object be unusually rich in radioactive elements? Let's check the math. To maintain 300 Kelvin at the object's estimated size, you need around 10 to the 14 watts of power generation. That's 100 trillion watts, continuously. Earth's entire internal heat flow from radioactivity and residual formation, heat is about 44 trillion watts. You need more than twice Earth's heat generation from an object that's far smaller than Earth. The concentration of radioactive elements would have to be absurdly high. Not just high, unphysically high. You can't pack that much radioactive material into that volume. It would be a critical mass problem. You'd create a reactor or a bomb, not stable heat generation. Tidal heating? Jupiter's moon Io is volcanically active due to tidal forces from Jupiter flexing Io's interior. This generates enormous heat. Could tidal forces heat this object? No. Tidal heating requires close orbits around massive bodies. This object orbits far from the Alpha Centauri stars. The tidal forces are negligible. They can't generate the required heat, not even close. Strike tidal heating from the list. Chemical reactions, combustion, or other exothermic chemistry releasing energy? This requires oxidizer and fuel. Space is mostly vacuum. What would it react with? And chemical energy per unit mass is limited. You'd need to be burning fuel at a furious rate to generate that much power. Where's the fuel coming from? How is it burning in vacuum? This doesn't work for anything beyond very short timescales. And remember, the object has been warm for at least 40 years. Chemical energy can't sustain that. Ruled out. Captured stellar wind? Maybe the object has a magnetic field that traps charged particles from stellar wind, heating it like radiation belts heat Earth's magnetosphere. Again, the distances involved make this impossible. Stellar wind is too diffuse at that range. Even with perfect trapping efficiency, which is unrealistic, you can't capture enough energy. The math doesn't work. Ruled out. Residual formation heat? Planets and moons start hot from the energy of accretion. They cool over time. Gas giants like Jupiter still emit more heat than they receive from the Sun, due to slow contraction and residual internal heat. Could this be similar? No, because the cooling timescale depends on size. Small objects cool fast. This object is at most hundreds of kilometers across. It would have cooled to equilibrium with space billions of years ago. Even if it formed hot, the heat would be long gone. Anything less than moon-sized cools too quickly. Ruled out. Every natural heat source fails. You can't maintain 300 Kelvin at that location with any known natural process operating over decades. This is not subtle. This is not a marginal problem, where maybe we're missing some factor of 2. The discrepancy is orders of magnitude. The object needs hundreds of trillions of watts continuously, with no obvious source. Thermodynamics says this can't happen naturally, yet it's happening. So either our thermodynamics is wrong, which seems unlikely given how well tested it is, or our measurements are wrong, which is possible but increasingly unlikely as multiple independent observations confirm the temperature, or the object is not natural. It's maintained at that temperature artificially. By design, through technology, this is where minds start to bend. Artificial heating implies intent, purpose. Someone or something chose to keep this object warm. Why would you do that? Thermal regulation for equipment, life support, maintaining materials at optimal operating temperatures. These are engineering reasons, not natural ones. And if you're engineering at this scale, in interstellar space, you're talking about capabilities far beyond anything humans have achieved. You're talking about an advanced civilization, one that can build kilometer-scale objects and send them between stars and keep them operating for decades or longer. The temperature paradox is the single strongest piece of evidence that this might not be natural. It's hard physical data. Thermodynamics doesn't lie. The object is warm. It shouldn't be. Natural explanations fail. Artificial explanation fits perfectly. This doesn't prove artificiality. Maybe there's a natural process we don't understand. Some exotic physics operating in ways we haven't discovered. But that's invoking unknown physics to save the natural hypothesis. When you have to invoke unknowns, you're reaching. The simpler explanation, using only known physics, is that the heat is generated artificially. That requires accepting the object is artificial, which is terrifying and thrilling in equal measure. But the thermodynamics are unforgiving. 300 Kelvin at tens of thousands of astronomical units from a star doesn't happen naturally. Something is keeping that object warm, and we don't know what, or rather, we might know but can't bring ourselves to say it. Spectrum analysis should have answered questions. It raised more. Every object in space tells you what it's made of through its spectrum. This is spectroscopy 101. Atoms emit and absorb light at specific wavelengths. The pattern of lines reveals composition, temperature, density, motion. We've been doing this for over a century. It works. The sun's spectrum shows hydrogen and helium absorption lines. Nebulae show emission lines from ionized gas. Planets show reflected starlight modified by atmospheric absorption. Every spectrum makes sense once you understand what you're looking at. Except this one. Webb took high-resolution spectra across multiple infrared bands. Near-infrared, mid-infrared. The coverage was comprehensive. What they got back was bizarre. The spectrum shows a continuum. That's the background emission across all wavelengths. On top of that continuum are features. Peaks and valleys, some broad, some narrow. This is normal. What's not normal is what the features are, or rather, what they're not. First pass analysis. Check if features match known molecules. Water has absorption bands in infrared. So does carbon dioxide, methane, ammonia, silicates. Hundreds of compounds have been measured in the lab. Their spectra are catalogued. Automated software can match observed spectra to databases and identify compounds. The software found nothing, no matches. The features don't line up with any known molecule. Maybe it's simple atoms, ionized hydrogen, neutral helium, heavier elements. Each has characteristic lines. Check the databases, nothing. The wavelengths of the features don't correspond to atomic transitions. Not in hydrogen, not in any element up and down the periodic table. Strike atomic emission. Could it be complex organic molecules? Long carbon chains or aromatic hydrocarbons, like those found in nebulae? These have complex spectra with many features. Maybe it's a mix creating a complicated pattern? Researchers tried fitting combinations, thousands of molecules mixed in varying ratios, searching for any combination that reproduces the observed features. The fitting algorithms ran for weeks on supercomputers. No combination worked. You could get some features to match by adding molecule A and some others by adding molecule B, but never all features simultaneously with any plausible mixture. The spectrum remains unmatched. What about exotic chemistry? Molecules we've never synthesized under conditions we've never studied? Compounds that only exist in weird temperature or pressure regimes? This is possible in principle, but we understand quantum mechanics well enough to predict spectra of hypothetical molecules. Even if we've never made a compound, we can calculate what its spectrum should look like. Researchers proposed exotic molecules, ran quantum chemistry calculations, predicted their spectra, none matched. You can keep inventing more and more exotic chemistry, but at some point you're just curve fitting, making up molecules specifically to match features. That's not science, that's speculation dressed as analysis. Then there are the narrow features, very sharp peaks and valleys at specific wavelengths. Natural emission and absorption lines can be narrow, but they're limited by thermal broadening and other physical effects. The narrowest features in this spectrum are sharper than should be possible thermally. They're resolution limited, as narrow as Webb's instruments can measure. This suggests the intrinsic line width is even narrower. How do you get such narrow spectral features? In laboratories, you use lasers, coherent light sources with extremely well-defined wavelengths. But this is an astronomical object. Natural astronomical processes don't create laser-like narrow lines, they create broadened features. Finding resolution-limited lines in an astronomical spectrum is weird, very weird. Some features show fine structure, not just a single peak, but multiple closely spaced peaks, like a line that's split into a triplet or quartet. Spectroscopic splitting happens due to quantum mechanical effects, fine structure, hyperfine structure, Zeeman splitting in magnetic fields. All well understood, but the splitting patterns here don't match known atomic or molecular physics. The spacings between subpeaks are wrong, the ratios are wrong. It's like seeing a musical chord where the harmonics don't follow any scale. Dissonant, unphysical, and the features are stable. Take spectra at different times, the features are in the same places with the same strengths. Natural emission can be variable. Changing chemistry or temperature shifts features. But these are locked, constant, unchanging over months of observation. This suggests whatever is producing the spectrum is stable, controlled. Not dynamic processes like chemistry or weather, but something fixed, something engineered. The word appears again. Engineered. If the spectrum can't be explained naturally, maybe it's not natural. Maybe the features are technological signatures, laser emissions at specific wavelengths, radio frequency leakage into infrared bands, thermal signatures from power systems. We don't know what alien technology looks like, but we know our technology creates specific spectral signatures. Artificial lighting, laser communications, heat from electronics, all leave marks. Could these features be similar? Alien technology operating in ways we don't recognize? This is where analysis becomes circular. You can't prove the spectrum is technological without knowing what alien technology looks like. But you can only know what alien technology looks like by finding it. Catch-22. What you can say is the spectrum doesn't match natural processes. Everything known from physics and chemistry fails to explain it. So either there's unknown natural physics, which is possible but increasingly ad hoc, or it's not natural. And if not natural, then artificial is the only remaining category. We're forced toward this conclusion, not because we want to, but because alternatives keep failing. Some scientists resist. There must be a natural explanation. We just haven't found it yet. Keep looking, try more models, more molecules, more physics. The spectrum will eventually make sense. This is the conservative position. And it's not wrong to be conservative. Extraordinary claims need extraordinary evidence. Spectral features that don't match known physics are interesting but not proof of aliens. More work is needed, more modelling, more observations at different wavelengths. Maybe X-ray spectra or radio observations will provide context. Maybe something in the optical will clarify. But months have passed. Dozens of research groups have analysed this data. Hundreds of spectroscopists have looked at it. Nobody can explain it. The spectrum remains anomalous, and the longer it remains unexplained, the more weight the artificial hypothesis carries. Not proven, not even strongly supported yet, but no longer laughable, no longer relegated to fringe speculation. Mainstream scientists are quietly, carefully, considering whether we might be looking at a spectrum produced by technology. The signal nobody can explain might be a signal that wasn't meant to be explained naturally. It might be a side effect of systems operating on a scale and with capabilities we can barely imagine. Or it might be natural, and we're just not smart enough yet to figure it out. Either way, the mystery deepens. The object is not stationary. This was clear from comparing observations across months. It moves, but how it moves is raising more questions than answers. In astronomy, everything moves. Planets orbit stars, stars orbit galactic centers, galaxies drift through space. Movement itself is not unusual. What's unusual is when movement doesn't follow expected patterns, when orbital mechanics don't quite work, when trajectories imply forces that shouldn't be there. And this object's movement is strange. Initial position measurements from Webb were compared to archival positions from decades-old observations. The object has moved across the sky consistent with being part of the Alpha Centauri system. This establishes it's gravitationally bound, not just passing through, but calculating the precise orbit requires multiple position measurements, spanning years or decades. With only sparse historical data and a few months of intensive Webb observations, the orbit is poorly constrained. What they can say is the object is moving in a way generally consistent with a very wide orbit around the Alpha Centauri barycenter, thousands of astronomical units out, orbital period measured in millennia, but the details don't quite fit. Orbital mechanics is precise. Given the masses of the stars and the observed position and velocity of an object, you can calculate its orbit exactly. The orbit is an ellipse, or in some cases, a hyperbola if the object is escaping. The parameters are well defined: semi-major axis, eccentricity, inclination. Everything follows from Newton's laws or Einstein's refinements. There's no ambiguity. Calculate the orbit from observations and you get an answer. When astronomers did this for the object, the answer was uncomfortable. The orbit is not quite closing properly. Here's what that means. Track an object over months. Measure its position and velocity. Calculate what orbit would produce that trajectory. Then predict where it should be months later. When Webb took follow-up observations, the object was not quite where predictions said, not far off. The difference is small, but it's statistically significant, larger than measurement uncertainties. The object is deviating from a pure gravitational orbit. Something is perturbing it, something is accelerating it in ways gravity alone doesn't account for. Could be measurement error. Positions at these distances are hard. You're measuring tiny angular shifts in the sky and converting to physical positions light years away. Small errors in measurement propagate to large errors in calculated position. The discrepancy could be noise, but teams have checked. Multiple independent position measurements from different telescopes, different analysis methods. The discrepancy persists. Within uncertainties, there's real deviation from a Keplerian orbit. So what could cause this? Natural perturbations, other objects in the system, gravitationally tugging on it. Alpha Centauri has planets. Proxima b and others, could their gravity explain the deviation? Astronomers modelled this, included all known planets. The gravitational effects are far too small. You'd need a much larger undiscovered planet, a Jupiter-sized world in the outer system. Possible, but there's no evidence for such a planet. And even a Jupiter wouldn't fully explain the observed perturbations. The effect is too large and in the wrong direction. What about the stars themselves? Binary star systems have complex gravitational fields. Alpha Centauri A and B orbit each other. That creates time-varying gravity. Could this perturb the object's orbit? Yes, but the effects are calculable. Include them in the orbit model. It helps, but doesn't fully resolve the discrepancy. There's still residual acceleration unaccounted for. Something else is acting on the object. Radiation pressure. Sunlight exerts tiny force on objects. It pushes on solar sails and affects comet trajectories. Could stellar radiation from Alpha Centauri A and B be pushing the object? At the estimated distance, and given the object's size and mass assumptions, radiation pressure is negligible. Orders of magnitude too small to explain observations, unless the object has an enormous surface area to mass ratio, like a solar sail. If it's extremely thin and light, radiation pressure could matter, but estimates of size and thermal emission suggest it's not a thin sail, it's bulky. Radiation pressure doesn't work. Outgassing. Comets accelerate due to jets of gas escaping as ice sublimates. The jets create thrust. Could this object be outgassing? There's no evidence, no spectral signatures of gas, no visible coma or tail. The thermal emission is too uniform. Outgassing creates uneven heating and visible plumes. None are seen. This doesn't look like a comet. Outgassing doesn't explain it. What's left? In conventional astrophysics, nothing. You've exhausted natural mechanisms. Gravity, radiation pressure, outgassing. That's the toolkit. If none explain the acceleration, you're stuck. Unless the object is accelerating itself, unless it has propulsion, thrust, and engine. This is the explanation nobody wants to voice, but that fits the data perfectly. If the object can change its velocity independently of gravity, the orbital deviations make sense. They're course corrections, maneuvers, controlled movement. This is extraordinary. It requires accepting the object is not just artificial, but actively controlled. Not a derelict drifting through space, but a functioning spacecraft under power. The thrust required is tiny, millinewtons, but sustained over months, small thrust accumulates into measurable velocity changes, and the direction of acceleration is suggestive. It's not random, it's not outward from the stars which radiation pressure would cause. It's tangent to the orbit, like a ship adjusting its trajectory, changing its path deliberately. Some researchers are exploring exotic natural explanations. What if the object has a magnetic field and interacts with the stellar wind in ways that create thrust? Magnetic sails are theoretically possible, but they require very specific conditions and create acceleration in specific directions related to the stellar magnetic field. The observed acceleration doesn't match this pattern. Magnetic sails are ruled out as not fitting the geometry. What if there's a dark matter wake or some other exotic physics causing drag or thrust? Now we're invoking unknown physics. Possible in principle, but completely speculative. There's no independent evidence for exotic forces in the Alpha Centauri system. You're inventing new physics solely to avoid the propulsion hypothesis. When you need to invent unknowns to save a natural explanation, the natural explanation is losing ground. The movement data doesn't prove propulsion. It shows anomalous acceleration that known forces don't explain. That's compatible with propulsion, but doesn't require it. Maybe there's a conventional explanation being overlooked. Maybe further observations will clarify. But right now, the simplest explanation for the movement pattern is that the object is under intelligent control. It's navigating, adjusting its orbit, going somewhere or maintaining a position. This aligns with the temperature anomaly and the unexplained spectrum. Each piece of evidence independently suggests artificiality. Together they build a case that's becoming difficult to dismiss. If it's true, if this object is maneuvering, then it's not just an ancient probe drifting through space. It's active, operational. Someone or something is flying it, right now, 4 light-years away, orbiting our nearest stellar neighbour, moving with purpose. This changes the question from what is it to what does it want? And that's a question that keeps people awake at night. The moment scientists suspected the object might be artificial, one question dominated. Is it transmitting? If this is a probe from another civilization, it might be sending data back to its creators or broadcasting to anyone listening. SETI, the search for extraterrestrial intelligence, has been listening for radio signals from space for decades. They found nothing convincing, but they've been listening for signals from distant stars, from civilizations light-years or hundreds of light-years away. This object is at Alpha Centauri, 4 light-years. If it's transmitting, we might actually hear it. Radio telescopes were redirected. The Very Large Array in New Mexico, the Green Bank Telescope in West Virginia, Parkes Observatory in Australia, FAST in China. Every major radio facility capable of pointing at Alpha Centauri was given time to observe the object's position. The search covered frequencies from megahertz to gigahertz, AM radio to microwave, looking for anything, any signal, narrowband carrier waves, broad pulses, modulation patterns, anything that didn't look like natural radio emission from stars or planets or cosmic noise. Weeks of observation produced terabytes of data, processed through algorithms designed to detect artificial signals. Looking for features nature doesn't create, narrowband signals are the classic SETI target. Nature makes broadband noise. Technology makes narrow carriers. The algorithms searched for sharp spectral peaks, for drifting frequencies that would indicate a transmitter on a moving object, for periodic pulses, for modulation that carries information. Nothing. The object is radio quiet at all observed frequencies. No detectable transmission, not even noise. It's remarkably silent. This is actually unusual. Most astronomical objects emit some radio waves. Stars have radio emission from their coronae. Planets emit at certain frequencies from interactions with magnetic fields and solar wind. Total radio silence from an object this size is rare, but the data showed nothing above background. If it's transmitting in radio, it's either below detection threshold or using frequencies outside the search range, or beaming in directions we're not seeing. Optical SETI looks next. Laser communications use light instead of radio. Much higher bandwidth. More power efficient for interstellar distances. If an advanced civilization wanted to communicate across light years, lasers make sense. Optical SETI searches for brief, bright flashes, pulses that stand out against the steady background. Telescopes, equipped with fast photometers, observe the object's position, looking for pulses on timescales from nanoseconds to seconds. Again, nothing. No laser pulses detected. The object's optical emission is faint reflected starlight only. No active transmission in visible wavelengths. Infrared. The object glows in infrared, but that appears to be thermal. Not a signal, not modulated, just steady, black body-like emission. No pulses, no patterns. The spectrum is weird, but it's not varying in time in ways that suggest information content. It's constant, unchanging, not a communication signal. X-ray and gamma-ray observations found nothing either. The object doesn't emit at high energies. No X-rays, no gamma rays. These are unlikely communication bands anyway. Interstellar medium absorbs high-energy photons, but for completeness, they looked nothing. So either the object is not transmitting, or it's transmitting in ways we can't detect. There are many possibilities: neutrino beams, gravitational waves, modulated particle streams, exotic physics we don't know about, communication methods far beyond our technology. If an advanced civilization has been traveling between stars, their communication tech might be incomprehensible to us. We're looking with the tools we have. If the signal requires tools we haven't invented, we'd never see it. Or maybe it's transmitting via laser, but the beam is tightly focused away from Earth. Laser communications can be highly directional, point-to-point links. If the probe is sending data back to its origin, and we're not in the beam path, we wouldn't intercept it. Imagine trying to eavesdrop on a conversation happening with flashlights between two people far away. Unless they point the flashlight at you, you see nothing. Same principle. The probe could be chattering away at its home base, and Earth is simply not in the line of communication. Some researchers suggested looking for leakage. Even tightly beamed communications leak a little. Scatter off particles, reflect off surfaces. Maybe we could detect side lobes or scattered light from a main beam pointed elsewhere. This requires extreme sensitivity. The leaked signal would be faint, but it's possible. Observations were attempted with the most sensitive receivers. Still nothing detected. If there's leakage, it's below our detection threshold. Then there's the possibility it's not communicating at all. Maybe it's a dormant probe, shut down, waiting for some trigger to activate. Or maybe it's a sensor platform, observing, collecting data, not transmitting, but storing, sending data in bursts occasionally, or waiting to be retrieved. If it only transmits once a year or once a decade, we might have missed the transmission. Continuous monitoring would be needed. That's expensive. Telescope time is precious. You can't watch one object continuously for months hoping it transmits, but targeted campaigns are ongoing, checking periodically, hoping to catch a transmission if one occurs. The silence is interpreted different ways. Skeptics say it supports the natural hypothesis. If it were artificial, it would be transmitting. Since it's not, it's probably natural. Believers counter that absence of evidence isn't evidence of absence. Just because we don't detect a signal doesn't mean there isn't one. Our technology might be inadequate. Our search might be incomplete. The probe might be designed for stealth. Or communication might happen in ways we haven't imagined. What about listening for internal sounds? If the object has machinery, does it make noise? Electromagnetic noise from electronics? Vibrations, could we detect these? At 4 light years with current technology, probably not. The signals would be impossibly faint, but in principle, if we could get close enough, an active machine would have signatures, humming from power systems, radio frequency interference from circuits, heat signatures from operating equipment. From across light years, these are invisible, but they're there if the object is active. Future, more sensitive observations might detect them. The search for communication continues. Every few months, another observation campaign targets Alpha Centauri, looking, listening, hoping. So far, the object remains silent. But silence doesn't mean absence. It might mean we're not listening the right way, or it might mean there's nothing to hear. The mystery deepens with every null result, because if this object is artificial and it's not communicating, what is it doing? Why is it there? What's its purpose? Questions pile up faster than answers, and the silence, rather than resolving uncertainty, makes everything more enigmatic. If the object is artificial, who made it? This question leads down a rabbit hole of speculation, but also reveals something important about the limits of our technology and imagination. Let's establish what we know. The object is at least 10 kilometers in its longest dimension, possibly larger. That's huge. For comparison, the International Space Station is about 100 meters across, the largest spacecraft humans have built. This object is 100 times larger, at minimum. Building something that big in space is beyond our current capability by a wide margin. Mass is unknown, but scale with size. Even if it's mostly hollow, a 10-kilometer structure has significant mass. Thousands of tons at absolute minimum. More likely, hundreds of thousands of tons. Getting that much mass into space is staggering. The ISS mass is about 420 tons. It took decades and dozens of launches to assemble. To build something hundreds of times more massive would require infrastructure we don't have. Mining asteroids for materials, orbital construction facilities, technologies we're decades or centuries away from. Then there's propulsion. If the object is maneuvering as the orbital data suggests, it has engines. Capable of sustained thrust over months or years, this requires fuel or some other energy source. Chemical rockets are out. The fuel mass needed for continuous thrust at this scale would be prohibitive. You'd need tanks bigger than the object itself. Nuclear propulsion is more efficient but still has limits. Fusion might work, or antimatter if you could produce and store it, or some advanced concept we haven't developed. Solar sails could provide thrust without fuel, but they don't match the observed acceleration direction and magnitude. This object, if propelled, uses technology beyond our current capabilities. Thermal control is another challenge. Maintaining 300 Kelvin in deep space requires either active heating or incredible insulation. Humans use radioisotope thermoelectric generators for deep space probes. Plutonium-238 generates heat, but the power density is low. You'd need tons of plutonium to heat a 10-kilometer structure. Not feasible. Nuclear reactors could work. Fission or fusion. Generate heat and electricity. Use it to maintain temperature. But reactors are heavy and complex. Engineering a reactor that runs for decades without maintenance in interstellar space is hard. We've never done it. Maybe an advanced civilization could, but it's not trivial even for them. Longevity is crucial. The object has been at Alpha Centauri for at least 40 years, possibly much longer. Human spacecraft degrade over decades. Electronics fail, materials deteriorate. We design for limited lifetimes, Because space is harsh. Radiation, micrometeorite impacts, thermal cycling, everything breaks eventually. For an object to remain functional across decades or centuries requires robust engineering, redundancy, self-repair capabilities, materials, science beyond what we have, possible in principle, but difficult. If humans built this, it would represent technology decades or centuries ahead of where we are now, and humans didn't build it. We know our spaceflight history. Every launch, every probe, we've sent exactly 5 spacecraft on trajectories that will eventually leave the solar system. Voyagers 1 and 2, Pioneers 10 and 11, New Horizons. None are going toward Alpha Centauri, none are 10 kilometers large. We didn't do this, so someone else did. Proxima Centauri has a planet, Proxima b. Could a civilization on Proxima b have built this? Possible, but there are problems. Proxima b is tidally locked. One side always faces the star, one side is eternal night. The star is a red dwarf, flare star. It emits powerful flares that would bathe the planet in radiation. Life could exist there, but complex technological civilization emerging is difficult under those conditions. Not impossible, just difficult. And if a Proxima b civilization built this object, why is it here? Why not orbiting their own planet? Why send it to orbit the Alpha Centauri pair? These are sun-like stars, more interesting than a red dwarf. Maybe they're studying them. Or maybe the probe came from elsewhere. Alpha Centauri, A or B, could have planets we haven't detected yet. Earth-sized worlds in orbits too close or too far for current detection methods. A civilization there could have built this. Makes more sense than Proxima b. Sun-like stars are better for life. Less radiation, more stable. If intelligent life emerged around Alpha Centauri A or B and developed space technology, this object could be theirs. Their satellite, their space station, their research platform. We'd be looking at their technology, alien engineering, 4 light years away. Or maybe it's not from Alpha Centauri at all. Maybe it came from farther away, built by a civilization dozens or hundreds of light years distant, sent here on a journey lasting centuries or millennia. Arrived at Alpha Centauri and entered orbit. Why? Maybe Alpha Centauri is strategically located, visible from many nearby stars. A good place to position a relay station or observation post. Or maybe the probe is mapping the galaxy, visiting star system after star system, collecting data. Alpha Centauri is one stop on a long itinerary. The probe might have visited hundreds of systems. Ours might be next. Or it already came and left. Or it's staying at Alpha Centauri because something there interests it. The engineering required to build and deploy such a probe tells us something about its creators. They have spaceflight capability far beyond ours. They can build large structures. They can send them between stars. They can keep them operating for extended periods. This implies a technological civilization at least hundreds of years ahead of us, maybe thousands. K2 civilization on the Kardashev scale, if you want to use that framework, capable of harnessing the energy output of their star for major projects. Building interstellar probes might be routine for them, easy, like us launching satellites. But why are we only finding this now? If they can build 10-kilometer probes, why don't we see more evidence? Where are the others? The galaxy should be full of their artifacts if they've been doing this for millennia. This is a variant of Fermi's paradox. If advanced civilizations exist and build probes, where are they? One answer, we're just starting to look carefully. This object was always there. We noticed it only because Webb gave us the sensitivity. Maybe there are more, around other nearby stars, waiting to be found, or maybe this civilization is rare, one of the few, or they're recent, just starting to explore, like us. Speculating about who built it is fun but ultimately unhelpful, without more data. What we can say is that if it's artificial, its builders have capabilities we lack. They can do things we can't, yet. That's simultaneously humbling and exciting. Humbling because it shows we're not the pinnacle of technology. exciting because it shows what's possible. If someone built this, we can too, eventually. We can aspire to build probes like this, send them to other stars, explore the galaxy. Not today, not this century probably, but someday. The object, if artificial, is proof that it can be done. That interstellar exploration is not fantasy, that civilizations can reach beyond their home systems and touch the stars, and if they did it, we can too. When the possibility arose that the object might be artificial, people wanted to send a message, contact it, attempt communication. If there's a probe from another civilization orbiting Alpha Centauri, shouldn't we try to talk to it? This impulse is natural, but it's also dangerous, and it's raised a debate that's been simmering in the scientific community for decades. Should we announce our presence to potential alien intelligences, or should we stay silent? The object at Alpha Centauri has brought this debate into sharp focus because it's the first plausible case where the question isn't theoretical. METI, messaging to extraterrestrial intelligence, is the active version of SETI. Instead of listening, you transmit. Send powerful radio or laser signals towards stars where planets might exist. Encode messages, mathematical constants, prime numbers, images, information about Earth and humanity. The idea is that if anyone is listening, they'll receive the message and know we're here. They might respond. METI advocates argue that passive SETI is too slow. If everyone just listens and nobody transmits, we'll never make contact. Someone has to take the initiative, send signals, announce ourselves, start the conversation. Critics of METI argue this is reckless. We don't know what's out there. Advertising our presence could be dangerous. If there are hostile civilizations, telling them where we are is foolish. We'd be revealing ourselves to potential threats. Better to stay quiet, listen, learn, only reveal ourselves once we understand the landscape. This is the silence protocol, advocated by scientists like Stephen Hawking, who warned that contacting advanced aliens could end badly for us. History shows that when civilizations with different technology levels meet, it often goes poorly for the less advanced. We should be cautious. The object at Alpha Centauri makes this concrete. If it's a probe, does it know about Earth? Has it detected us? If it has, transmitting is moot. They already know we're here. But if it hasn't, sending a signal would reveal us. The probe might be dormant, waiting for a signal to trigger it awake, like a motion detector, silent until something moves. Then it activates, transmits, alerts its creators that it's found something interesting. Do we want to be that trigger? Do we want to wake it up? Some scientists argue the probe almost certainly knows about Earth already. It's at Alpha Centauri, 4 light years away. It has line of sight to the solar system. If it has any kind of sensors, it can see us. Earth's atmosphere has been oxygenated for billions of years. Oxygen is a biosignature, detectable spectroscopically. Our radio and television broadcasts have been leaking into space for a century, spreading at the speed of light. Proxima Centauri and Alpha Centauri received Earth's first radio broadcasts decades ago. If the probe is listening, it knows we're here. We can't hide. Transmitting doesn't change anything. Others counter that passive detection and active signaling are different. The probe might not have good sensors. It might not have analysed Earth's atmosphere. Radio leakage is faint and omnidirectional. Easy to miss unless you're looking carefully, but a directed, powerful signal straight at the probe, that's unmistakable. That's us raising our hand, shouting, "Here we are," could be different from being passively detectable, could trigger responses we don't want. The debate has raged for months among scientists and government officials. Organisations that manage radio telescopes have policies. Before transmitting any METI signal, there should be international consultation. No single group should unilaterally announce humanity's presence. But there's no binding agreement, no law. The Outer Space Treaty doesn't cover this. If someone wants to transmit to Alpha Centauri, they technically can. Some groups have proposed doing exactly that, broadcasting messages toward the object, hoping for a response. Governments are nervous. If there's a possibility the object is artificial, they want coordination. NASA and ISA issued statements urging caution. The United Nations Committee on the Peaceful Uses of Outer Space discussed it, but there's no consensus. Scientists are divided. Some want to transmit immediately, others want to observe more first. Wait, learn, understand what we're dealing with before acting. The window might be closing. If the probe is maneuvering, it might not stay at Alpha Centauri indefinitely. It could leave, opportunity lost, or it could be there for millennia. Rushing is foolish. Meanwhile, amateur radio operators are not waiting for permission. Powerful amateur transmitters can send signals to Alpha Centauri, not as strong as professional radio telescopes, but detectable in principle. Some have already transmitted short messages, math, music, images of Earth. Whether the probe could detect these weak signals is unknown, but the transmissions happened, uncoordinated, uncontrolled. The silence protocol, to the extent it ever existed, is breaking down. The question is no longer whether to transmit, but who gets to decide and what to say. This raises ethical questions. Does humanity have a right to silence? If some want to contact aliens and others don't, who wins? This is not a decision that should be made by a few scientists or governments. This affects everyone. If contact goes badly, we all suffer. Shouldn't there be global consensus? A vote? How do you get 7 billion people to agree on anything, let alone something this unprecedented? The practicalities are overwhelming, so decisions are being made by small groups, scientists, governments, amateur enthusiasts, each doing what they think is right. The collective outcome is chaotic, and all of this assumes the object cares about our transmissions. Maybe it's not listening. Maybe it doesn't respond to radio. Maybe it's programmed to ignore primitive civilizations like ours until we reach some threshold of advancement. Or maybe it's already transmitting back and we're not detecting it. The silence might not be ours to control. The probe might have its own agenda, its own protocols. Trying to second-guess alien engineering is futile. We're projecting human assumptions onto something that might operate on completely different principles. What seems clear is that the discovery of this object has changed the METI debate from abstract to immediate. For the first time, we might be able to send a message to something real, not a hypothetical civilization around a distant star, but a physical object we can see, that we photographed, that's definitely there. Whether we should is not settled. Whether we will is almost certain. Someone will transmit, maybe already has, and then we wait. 4 years for a signal to reach Alpha Centauri, 4 years for a response to come back, 8 years total. If the probe responds, we'll know by the early 20s. If it doesn't, we'll still be uncertain. Silence could mean many things. Not interested, not capable of responding, not there despite appearances, or listening carefully, deciding what to do about the noisy neighbours 4 light years away who just announced themselves. Stop and think about what it would mean if this object is artificial, not speculative, not hypothetical, confirmed artificial, proven to be built by non-human intelligence. The implications cascade through every aspect of human civilization. Science, philosophy, religion, politics, nothing remains unchanged. We've imagined this moment for centuries. Science fiction explored it. SETI prepared for it. But imagination is not preparation. The reality would be overwhelming. First, it confirms we're not alone. This is profound. Humanity has wondered about life beyond Earth since we understood Earth was not unique. Are we it? The only intelligence in the cosmos? The only civilization? The only ones asking these questions? Confirmation that others exist changes our self-perception fundamentally. We're not special, not unique, just one among many, or at least one among two. This is humbling. It dethrones us from any assumed centrality. Copernicus did this for Earth's cosmic position. Darwin did this for humanity's biological status. Confirming alien intelligence does this for our existential uniqueness. Second, it proves interstellar travel is possible. Not just theoretically possible, but actually done. Someone built a probe and sent it to another star system. They solved the engineering challenges we're still grappling with. Propulsion, life support for long journeys if the probe carries crew, self-sufficiency for decades or centuries. They did it. This means we can too. It's not a fantasy, it's achievable. Knowing something can be done changes the calculus. Investment in interstellar research might increase. If they did it, we must be able to as well. National prestige, scientific ambition, the desire to match or exceed alien capabilities. These could drive space programs in new directions. Third, it raises questions about alien intentions. Why build this probe? Why send it to Alpha Centauri? What is it doing? Is it observing us? Earth is visible from Alpha Centauri. A probe there could study the solar system, watch Earth, monitor our development. This is unsettling. We might be under surveillance. Our privacy, on a cosmic scale, violated. Everything we do visible to watchers 4 light years away. Or maybe the probe has nothing to do with Earth. Maybe Alpha Centauri is the target. Something about those stars interests them. We're incidental, irrelevant. Beings who happen to live nearby but aren't the focus. That's somehow more unsettling. Being ignored, not important enough to monitor. Fourth, it forces confrontation with our technological limitations. If the object is artificial, and we can't even determine that definitively, it shows how primitive our capabilities are. We can't analyze it properly from 4 light years. We can't communicate with it reliably. We certainly can't visit it. We're limited to passive observation, like Bronze Age humans, watching jets fly overhead. We can see them, we can describe them, but we can't understand them or interact with them meaningfully. The gap between us and the probe's builders might be vast, centuries, millennia. They're doing things we can't, won't be able to for generations. This is sobering. We like to think we're advanced, we have sophisticated technology, but compared to an interstellar civilization, we're children, barely out of the cradle. Fifth, religious implications are enormous. Most religions have cosmologies that assume humanity is central, created by God or gods with special purpose. Many don't explicitly address alien life because the concept wasn't in the cultural context when the religions formed. How do belief systems adapt? Some theological frameworks easily accommodate aliens. God created them too. They're part of divine creation. Other frameworks struggle. If humanity is unique in God's plan, what does alien intelligence mean? Are they also made in God's image? Do they have souls? Did Christ's sacrifice apply to them too? These are not trivial questions for billions of believers. The discovery could trigger theological crises, or it could be integrated smoothly. Hard to predict, but indifferent it cannot be. Sixth, geopolitical consequences. Who speaks for Earth? If the probe responds to a transmission, who represents humanity in that exchange? The United Nations? The country that transmitted? Scientists? Some new global organization? We don't have structures for this. We've never needed them. But if communication becomes possible, decisions must be made. Fast, under pressure, with stakes that couldn't be higher. Miscommunication, misunderstandings, sending the wrong message, any of these could have consequences. We need protocols, agreements, international cooperation on a level we've never achieved, over something unprecedented. Good luck. Seventh, impact on culture and society. Science fiction becomes less fictional. All the stories, all the speculation about aliens and first contact, suddenly relevant, templates for how we might react, for what might happen. This could be inspiring or terrifying depending on which stories you remember. Independence Day or Star Trek, War of the Worlds or Close Encounters. Culture would absorb this, process it. Movies, books, music, art, all reflecting on what it means that we're not alone, that something is out there, watching, waiting. The zeitgeist would shift. How far and how fast depends on how the discovery is communicated and what else we learn. 8th, scientific revolution. Astronomy, physics, biology. Every field would be affected if we learn anything about the probe's composition, materials, propulsion. That's new physics, new engineering, things we don't know how to do, potentially revolutionary technologies. If we detect life, or even just confirm technological activity, that's exobiology confirmed. The study of alien life becomes real science rather than speculation. Funding priorities would shift, resources poured into trying to understand alien technology. Trying to bridge the gap, this could accelerate human technological development, or distract from other important work, or both. The implications are so vast that even listing them is daunting. This isn't like discovering a new particle or a new planet. This is discovering we're not alone, that other minds exist, other civilizations, that the universe is inhabited, teeming with intelligence, or at least not empty of it. We don't know if we're in a crowded galaxy, or if this is the only other civilization nearby. But even one changes everything. The question, are we alone, has haunted humanity for millennia. Confirming the answer is no would be the most important discovery in human history. Bar none, everything else is footnote. This is the main event, and we might be living through it right now. The object at Alpha Centauri might be the proof we've waited for, or it might be natural, a bizarre natural phenomenon we'll eventually explain. But the possibility that it's artificial, that we're seeing evidence of another intelligence, that changes how we view the cosmos and our place in it, permanently, irrevocably, and we're only at the beginning of understanding what that means. In the end, after all the data, all the models, all the debates, all the speculation, humanity arrives at the same place it always does when confronted with the truly unknown. We wait. The object remains at Alpha Centauri, warm, silent, unclassifiable. Webb continues to observe it when time allows. Other telescopes check in periodically. The data trickles in. Nothing dramatic changes, no sudden acceleration, no obvious transmission, no unmistakable proof that ends the debate one way or the other. Just the same anomalies, the same questions, the same uneasy possibility. Some scientists grow frustrated. They want answers now. Better instruments, dedicated missions, ambitious plans are proposed. Interstellar probes of our own, solar sail flybys that could reach Alpha Centauri in decades, not centuries. Not to intercept the object, far beyond our reach, but to get closer. Reduce the uncertainty, turn speculation into measurement. These projects are expensive, politically difficult, but momentum is building. Because once you know something like this might exist, it's impossible to unknow it. Others counsel patience, caution. Time is on our side, they argue. The object has been there for decades. It's not going anywhere quickly. Rushing could lead to mistakes. Better to observe, learn, improve our understanding of natural physics before declaring anything artificial. History is full of anomalies that turned out to have mundane explanations once technology caught up. This could be another one. We should not let our imaginations outrun our evidence. The public lives in between, half fascinated, half anxious. Media cycles flare up whenever a new paper is published, then fade. Life goes on. People still go to work, still fall in love, still argue about politics and sports and money. The possible presence of alien technology 4 light years away doesn't change rent prices or grocery bills. Not yet. The human mind is good at compartmentalization. Cosmic awe fits awkwardly into daily life. And yet something has shifted. A quiet awareness settles in. A sense that the universe might be watching back. That the stars are not just distant nuclear furnaces, but potential homes of intelligence. That the night sky is not empty in the way we once assumed. Somewhere between Alpha Centauri A and B, something is warm when it shouldn't be, moving when it shouldn't, emitting light that physics can't easily explain. Maybe it's natural, and we'll figure it out someday. A new class of object, new physics, a reminder that the universe is stranger than our theories. Or maybe it isn't. Maybe it's a relic of another mind, a machine built with purpose, sitting quietly at our nearest neighbouring stars, not hiding, not announcing itself, just there. If so, then the most remarkable thing is not that we found it, it's that it was always there, 4.37 light years away, close enough to be neighbour, far enough to remain unreachable, a silent presence at the edge of our awareness, waiting while we learned how to see. And now that we have seen it, the waiting has only just begun.